So let's go ahead and define our constructor here. So we have a parameterized constructor who's going to have two parameters, size, and which will be of type size t, and it val, which is going to be of type integer. Followed by that, we're looking right over here. We can see that there is an initializer list where we are taking the values passed into this function, and we're going ahead and using them to initialize the private data members here. Notice that I'm starting array out with the value of null pointer. I'll explain why that is here in a second, but anytime we're kind of going about grabbing a resource, we're going to make that grab within the actual body of this function opposed to doing it within the initializer list. So to set things up, I'm just initializing, giving an array a well-defined starting value, which is simply 0 or the null pointer. I'm going ahead and initializing the size data member with size passed to this function, and I'm going ahead and taking the capacity and simply having it start out as size multiplied by 2. And the reason for this is it will go ahead and provide some room if we'd like to add additional elements into the array pointed to by the object that's being constructed. Okay, so let's go ahead and get into the body of this function, which is, I know it's kind of crunched here, but it's going to fall between these two curly braces. So why didn't we acquire the array on the free store within the initializer list? We could have wrote where null pointer is. We could have wrote new int of, in this case, size times 2. Why didn't we do that? Well, we're requiring a resource, and it's not for certain that that acquisition is going to necessarily go as planned. So in this case, I've decided to surround the request or the attempt to acquire that resource within a try-catch block. So in this case, what I'm reading here is I'm trying to get a new array of capacity from the free store manager. It could be that an exception is raised during that process, and that maybe there is no memory available. And in that case, an exception of type standard library bad allocation would be thrown. Now, notice here, there's really not much we do, because if we didn't acquire the resource, we don't have anything necessarily to clean up. So we could just go ahead and rethrow that exception. But maybe, or I guess in a different type of class, let's go ahead and say, maybe we were defining a class that had more than one dynamically allocated object, and the first allocation succeeds, but the second allocation fails. Well, because that first allocation succeeded, we'd have to go ahead and, when the exception was raised, go ahead and catch the exception, deallocate the memory that was allocated in the first allocation, and then rethrow the exception to let the caller know about the error. So that's kind of why I'm structuring it this way, is it's not guaranteed that these acquisitions are going to succeed. And if we want to do anything to accommodate an exceptional condition, we really have to have this in the body so we could provide the code that would handle that. Finally, the last thing we're going to do within the constructor is going to initialize the array. So remember, if we request something from the free store manager, what we get back is some memory we can use. In this case, it would be a contiguous allocation of capacity and number of integer objects, but it's not clear what's in those. It's kind of whoever used them last, we'd go in and we could find their stuff. So to allow our objects of type vectorint to start out in a well-defined state, the last portion of the constructor here is going to be to call a private member function. So one that will support the implementation of the constructor. And I'm going to go ahead and pass it init val, and its whole purpose here is going to be to go from 0 to size. So each of the valid positions or occupied positions within the dynamically allocated array, and go ahead and assign them that initial value. And at this point, if we were to call, say, vector int v1 or vi of 2, 0, The composition of this object is going to then be array, size, capacity, little table here. This will point out to an array of 4 elements. The first 2 are going to be initialized with the value of 0. The other ones, who knows, but we requested a vector of size 2. So 2 will be reflected there, and then 4 in the sense that if we were to push back additional values to this to VI, we'd have 2 slots available until we needed to perform a resize operation. Okay, the destructor for objects of this type is going to be pretty simple. If you recall, a destructor is simply going to be, the name of the destructor is simply the name of the class, so vectorint. It is one of those special functions who does not return a value and prefix the name of the class. We have this squiggly line here. So vectorint is the name of the destructor, and its parameter list is always going to be empty. We go ahead and provide the definition of this special function that is invoked implicitly if our object resides in the stack, or implicitly if it's on the free store and delete is invoked on its address. So in this case, when the destructor is fired off, we simply want it to deallocate the memory associated with the address stored in array. And that would go ahead and tear it down. And look here, if we're using vector event, we no longer have to worry about any calls to new or delete, because the constructor and destructor respectively are worrying about that for us. Okay, the fun function, push back. We'll go ahead and get into that here in 1 second. Okay, so pushback is going to resemble the standard library vector, and hopefully this implementation will help you understand more or less what's going on there. So pushback is going to take the integer value, which we like to add to the vector. In the case, now remember, size is kind of telling us the next open slot. So if we have, say, that vector that we talked about previously of capacity 4, so say they're all initialized with 0, and size is going to kind of point to here. So that's 0, 1, 2, 3, 4. Capacity is referencing the top. Notice that on a pushback operation, if size is not at capacity, we have an open location in this array. In that case, we can go ahead and let's say we push back the value of 7. We can add it to R of size, which would in this case be R of 2. Notice how size is effectively communicating the top position or the open position within this array. And then we can increment size by 1 to show that size is now, there are 3 elements stored within this array. The cool thing about this again is size, because of 0 indexing, there are 3 slots or 3 elements within our array occupying indexes 0, 1, and 2, and the open index is going to be at slot 3. So the final thing here is we're just returning a self-reference. We talked about that a little bit in a earlier lesson, so I'll go ahead and skip over that quick. But let's say we have an additional pushback to this vector here. If we added, say, pushback 8, at that point, size would now be equal to capacity. And we would have to perform some sort of resize if we wanted wanted to add another element to this array here. So that's going to be this part here. I've defined 2 private helper functions to support the resize operation. One is going to be grow, which is simply going to call resize with an argument of capacity times 2. The fun one is going to be how resize is defined. And this is nothing you haven't seen before. The only difference here is that we're seeing it happening within an actual class. So what's going on? So resize is going to take a size t argument, which is going to specify the new capacity of array. So in this case, array pointed to, let's say, that array of 4 integer objects. In the case of calling, say, grow, we're going to need to create a new array of 8 objects. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we want array to, at the end of this, to point to that new dynamically allocated array. So the first thing we're going to do is create this thing right here. To do that, we're going to call new, and we're going to store its address in some sort of temporary pointer. In this case, I'm calling it CPY as short for copy. The next is going to be to determine the number of objects we're going to copy over from the original array, which is R. So num2 copy this is where it can get interesting. So I'm assuming that resize could also be used to shrink the array. And let's say the new capacity is 2. So 2. If the new capacity was 2 and not, say, 8, in that case, we could only store 2 of the elements from the original array into the newly allocated array. So in that case, num2 copy is going to essentially be governing the for statement, which will carry out this copy process. It'll be the conditional at the top end of the process. So num2 copy is going to be assigned size. So the previous number of elements that were contained within this array, if new capacity is greater than size. Otherwise, we'll go ahead and simply assign the new capacity. So in the case of going to this red here, where the new capacity was, say, 2, num2 copy would have to be, whoops, num2 copy would be 2, because we only have 2 positions available. If new capacity is 8, num2 copy is going to be equal to 4. Why is it 4 and not 8? The original array only had 0, 1, 2, 3 indexes available for a total of 4 elements. And we simply want those 4 elements to get placed into the corresponding fields of the newly dynamically allocated array. And to just, I guess, point this out a bit more explicitly, that position comes from there, this one from here, that one goes there, and finally, the last one gets placed at the corresponding index in this newly allocated array. Now, if we were going the other direction, we'd only be able to place these 2 elements here. I think that's the right shade of blue. So at the end of this copy procedure, we can go ahead and deallocate the previous array. So we can go ahead and deallocate that one, and then we can update array's pointer from pointing to the old one to pointing to this new one. Thereafter, we need to update the size, because remember, the size could have got smaller and we could have lost some data. So size gets assigned to num2 copy. Thereafter, we need to update capacity as well to the new capacity. So let's go ahead and just run through this quickly and see what happens. So we're going to be using the parameterized constructor followed by extensive use of the pushback function. So let's say we start out, create a new vectorint vi with a single object within it. So VI is going to be initialized with one slot within an array of capacity 2, and we're going to initialize that value to 0. Now notice here size is 1, capacity is 2. So we have one of 2 spaces filled. On a call to pushback on V1, pushing the integer value of 2 to that array, we can see here that, okay, in this instance, there is space available, so it will be added to the end of that array. At this point, size is equal to capacity. And if we would like to push back an additional element to that array, a resize operation will have to happen. So next thing we're doing is vi.pushback11. So at this point, size is equal to capacity, so we call that grow function. Notice here that after this operation, the base address of the array has changed. Why has it changed? Because remember, we just defined the resize function to actually go out and get a brand new array and actually assign the address to that array to copy after deleting the original array. So that's why there's the difference here. By the time we get to here, memory has been deallocated for that old array. Now we're at size 3, capacity 4, because the capacity, as we've defined our resize function, simply doubles. So we can have an open slot, one open slot, we can go ahead and push back the integer value of 7. So at this point, notice that the addresses here are the same because we have not had to perform any sort of resize operation, right? Okay, but at this point, capacity and size are equal. So if we do an additional pushback, we're going to need to go out there and get a new array with twice the capacity, copy the things over, deallocate the previous array, and update that array pointer. And when we do vi.pushback21, just that happens. We can notice here that there is going to be a new array formed, and we can tell that by the base address. So this is V1's array. We can see that its size is 5. Furthermore, we can see that it has a capacity of 8, so 3 open spots. And at the end of that resize function, the previous array would have had its memory deallocated, and array would be pointing to this dynamically allocated object with 5 equivalent to size, 8 is going to be capacity. So hopefully this walkthrough has kind of helped. Again, this is just showing how the array of V1 has changed throughout the lifetime of this object, and what has been shown within each of these ASCII boxes or rows of data, as you've seen here, is simply that as we go through, we're only showing the elements or the integer objects currently residing within its array. And as size equals to capacity, hopefully it's clear here that we can see that a brand new array has its memory allocated for the contents of the old array are copied over. The pointer of array gets that private data member gets updated to reflect that newly allocated, dynamically allocated array.